Today's lecture will focus on the construction and interpretation of confidence intervals. So I think what you'll find as we get into the concept of a confidence interval is I think you'll find that the idea of a confidence interval is really pretty straightforward in terms of its application and how we use it and how we calculate it. Really, the hard part with these inferential statistics is really the part that we've covered, which is how does all the probability work and make these things fit together so that we can actually control and calculate the error involved whenever we go to estimate a parameter. So we've covered a lot of that. So today is really a focus on the actual computation and an interpretation of confidence intervals, along with just kind of whenever we change some values in a confidence interval, what happens? So what are the effects of some of the different components of a confidence interval, and just a little bit about kind of where it comes from, but we've really already covered that material. So I think you'll find that actually the calculation of a confidence interval is not that bad. The other thing that I should mention here is we've actually already done confidence intervals in this class because way back in the first unit, we used 1 over square root of n in order to estimate the margin of error for a proportion. So if you remember doing that, we would take the proportion and we would add and subtract that margin of error, 1 over square root of n, and we would create this interval. And this interval, we would say we're 95% confident that the population proportion is within this interval. That's all a confidence interval is. Now, the thing that we're going to be able to do at this point, now that we've dealt with some of the mathematics of it, is we're going to be able to talk about how we change that confidence level, and we can talk about how we more accurately calculate that margin of error, or as I will typically call it, that error tolerance. So that's really the focus of what we do today. I'll also mention at the end, I'll just kind of show you where that 1 over square root of n formula comes from that we used at the beginning in order to estimate that margin of error for a proportion. As we said before, it's a conservative estimate, but it's not an exact value. So today we'll be able to calculate a much better value for that margin of error. So anytime you deal with confidence intervals, of course, these are inferential statistics, so you're not going to be 100% confident. So when you do a confidence interval, you can't be 100% confident. Technically, a 100% confidence interval is always the same. It's negative infinity to positive infinity. You're 100% sure that the parameter is somewhere on the real number line, but that really doesn't tell you anything. So in order to narrow down where the parameter is and create some interval that's not just the whole number line, to narrow that down, we have to be something less than 100% confident. So you can pick any confidence level you want, technically, but there are some common confidence levels that we tend to choose in statistics, and these are the ones that I will ask. I do ask you to do a 50% confidence interval when you do the lab, but it's just a matter of clicking a button in the software. But for the most part, anytime I ask a confidence interval question, I'm going to ask you either 90%, 95%, or 99%. These are just the common confidence levels that we use in statistics, and these are the ones that we will use for this class. Now, of course, if you want a 97% confidence interval, you can calculate that, but you would have to figure out what the z-value is in order to get that confidence level. So the confidence level really does tell you what the z-value is. So these are important values. You don't really have to memorize them, but you need these somewhere written down, convenient to you, that you can reference them when you're doing confidence intervals. Because anytime you do a 90% confidence interval, your z-value is going to be 1.645. If you do a 95% confidence interval, it's going to be 1.96. And if you remember from the empirical rule, we said 95% of data is within 2 standard deviations. So if we're a little more accurate than just that value of 2, it's actually 1.96 standard deviations for the normal distribution. That 2 is really comes from a rounded value. If you actually got 2 standard deviations, you actually get 95.44% of your data. So to get that exact 95%, you need 1.96 standard deviations. And to get 99%, you need 2.576 standard deviations. So I'm not going to get too technical here, but you will notice that I subscript all these z's with alpha over 2. You don't really have to do that. Alpha in a confidence interval is basically the probability that you're wrong. So in a 90% confidence interval, there's a 10% chance you're wrong. So alpha is 10% or 0.1. In a 95% confidence interval, alpha is 5%. And in a 99% confidence interval, alpha is 1%. All confidence intervals are also what we call two-tailed, meaning that there's error on both sides. And the reason why there's error on both sides of a confidence interval is because when you create an interval, there is a probability that the actual parameter is below the interval that you calculate, and there's also a probability that it's above the interval that you calculate. So there's error on both sides of the confidence interval. So because of that, we always divide alpha by 2. So really, for example, if you're 95% confident, that actually means there's a 2.5% chance that it's below the interval and a 2.5% chance that it's above the interval. So these z-values are what you would expect. They're standard normal values. And where they really come from, I'm just going to use the 95% to illustrate. But basically, if you want to be 95% confident, or if you look at a standard normal distribution, what you will find is you will find that 95% of your data is within 1.96 standard deviations. So if you understand the standard normal distribution, you can see where these values come from. These are just standard normal values. And technically, if you want to be technical about it, if you calculate the probability that a randomly selected z-value is between negative 1.96 and positive 1.96, you will get 95%. So that's really mathematically where that 95% confidence comes from, why we use a z-value of 1.96. If you want to see it graphically, I think that's the easiest way to actually see this and understand it. This is your standard bell-shaped curve. It's a z-distribution. It's symmetric about 0, standard deviation of 1. And it just lays out for 95%. It lays out that if you look between two z-values, a negative 1.96 and a positive 1.96, within that interval, you will find 95% of your data. That's a 95% confidence interval. That's why we use 1.96. That does mean that there's 2.5% of error in each tail. So the area in each tail is, you can see I have it signified there as alpha over 2. That's why we say alpha over 2, because we always subscript z technically by whatever's in the tail of the distribution. So I'm not really worried about the subscripts. We'll typically just write z. Z will stand for whatever, based on whatever confidence level you're dealing with. But this is just an illustration. You can also see I wrote it out more generally. If you want to be technical in terms of alpha, the area in the tails are alpha over 2 in each tail. And then the area between the two z-values is always 1 minus alpha. And with some algebraic manipulation, you can actually write a probability statement for this. And if you algebraically manipulate it, then you can come up with a formula for the confidence intervals, which we're going to use those formulas, but I'm not actually going to derive them for you. That's beyond what we do in this course. But that picture is nice to understand. It's nice to understand where these z-values come from and why am I able to be 95% confident. And the reason being is because we know through this z transformation, and we can transform like a mean into a z. We've already done that. We did that in the last section. So because we can do that, we can figure out an interval that's going to allow us to say we're 95% sure that the parameter is within that interval. Okay, so let's jump into an example. So here's our first example. In a simple random sample of 150 households, the sample mean number of computers was 1.32. We're going to assume the population standard deviation is 0.41. So what you'll notice is anytime we deal with the mean, we're always going to assume that we know the population standard deviation. You might think that that's not really realistic, and you're correct, it's not. If you don't know the population mean, you're probably not going to know the population standard deviation. The only way to know the standard deviation would be to have the whole population. If you have the whole population, you can just calculate the mean. You don't need to estimate it. But mathematically, this is really where we start with confidence intervals. We start with the scenario where we assume we know the population standard deviation. Ultimately, what you'll do in these cases is you will estimate the population standard deviation with the sample standard deviation. But that does create a few issues and makes things a little more complicated mathematically. So it is something that we don't deal with mathematically in this class. But basically, when you don't know the population standard deviation, really what you're going to end up doing there is you're going to end up estimating it with the sample standard deviation. But for our purposes, we're going to assume in these kinds of problems that we actually know what the population standard deviation is. Okay, so construct a 95% confidence interval. So this is your typical problem. So I'm going to tell you what the confidence level is. In the problem, you're given all the information you need. You're going to need three things. You're going to need, well, for this kind of problem. This kind of problem is based on the mean. So we're going to need the sample size, we're going to need the sample mean, and we're going to need the standard deviation. Those are the things that we need, along with how confident we are. If we know that, then we can figure out this confidence interval. So when you do read this problem, it is important that you recognize that this is for the mean, because we will do two different kinds of problems in this class. We will estimate both a mean and a proportion. So it is important that you recognize that this is the mean. So when you see it's a mean problem, make sure you use the correct formulas for the mean. If it's a proportion problem, then you have to use a different formula. I like to start just by jotting down what I know from the problem. So let me start there. Whenever I read this, it says a sample size of 150 households. So that's my sample size. That is N. This sample yields a mean of 1.32. So that's my sample mean. X bar is 1.32. We also are given that the population standard deviation, that sigma, is 0.41. That, along with how confident I am, is everything I need to know in order to figure out a confidence interval. So this is not all that different than what we did way back when we used 1 over square root of n as an estimate. Basically, we need our statistic first, which we have because we know that x bar is 1.32. Once we get our statistic, then we're going to have to figure out how much error I would expect in that statistic. That's my error tolerance E. Sometimes people will also call this margin of error. So we need to next figure out the error tolerance. Then we're going to add and subtract that from the parameter. So the error tolerance for the mean is always calculated. It's always z times the standard error. The standard error we covered in the last section, which is sigma over square root of n for the mean. So you basically take z times sigma over square root of n. Remember, sigma over square root of n is the standard deviation. So we basically need, to be 95% confident, we basically need 1.96 standard deviation. So we take 1.96 times the standard deviation. That's really where this formula comes from. Not like I'm going to ask you that, but that is really where the formula comes from. These error tolerances are always just your distribution value, and in our case is z, times the standard error. So as you can see, I already have the values plugged in here. So we know we want a 95% confidence interval, and that's why that list of values on that last slide are so important. It's very important that you have those values, so we know that when we're 95% confident, we're going to use z equals 1.96, and that's for the reasons that we talked about before. 95% of observations in a standard normal distribution are between negative 1.96 and positive 1.96. We multiply that by the standard error. If we plug in for sigma, the standard deviation is 0.41. The sample size in this case is 150. So we crank through the math there, and that gives us our error tolerance of 0.066. So that's all there is to calculating the error tolerance. Now, once you get that error tolerance, then you take your statistic, in this case x bar, our sample mean, and we're going to add and subtract that error tolerance. That's going to give us our interval. So our x bar value is 1.32. We just calculated our error tolerance to be 0.066. And of course, we're going to write this in interval notation, just as we had done before. So you basically write it as an ordered pair, just use parentheses. The lower value goes first, and then the higher value goes on the right. And that's how you create your interval. So in this case, our interval is 1.254 to 1.386. And of course, you get that by taking 1.32 minus 0.066, and then you take 1.32 plus 0.066, and that gives us this interval. So that's really all there is to the calculation of a confidence interval. You just have to make sure you pick out the proper values you need from the question. Make sure you know what those z values are. When you see 95%, you need to make sure you know that that's 1.96. And then you just plug into these formulas, crank through the math, and you're going to be able to get your confidence interval in that way. There's pretty much always a second part to confidence interval questions. I really like to ask you to also interpret them. Because it's not enough to just be able to say this is what the confidence interval is. You need to also understand what that confidence interval means. So basically what a confidence interval does is it estimates a parameter. So we use x bar to estimate mu. That's the idea here. We're using our sample mean to estimate our population mean. But what we know is that our sample mean is not going to be exactly equal to our population mean. The probability of that is actually theoretically 0, but if it's a continuous scale. What we have to do in order to create some confidence, in order to create a high level of confidence, like in this case 95%, is we have to create an interval. And then we're going to be able to be confident, in this case 95%, that the parameter is within that interval. So statisticians much prefer interval estimates over just a single point as an estimate, because a single point is not typically going to be right, but a confidence interval or an interval, we can be very confident that our parameter is within that interval. So that's what we're going to start with. You always start, in this case we're 95% confident, so we're going to say we are 95% confident. And we're going to say that the parameter is within the interval. There's 3 things that you say: how confident you are, what the parameter is, and say it's within the interval. So your statement here is going to be something like this: we are 95% confident that the population mean number of computers per household is between 1.254 and 1.386. So I will always write these in the same form. The main thing is that you have those 3 main components in there: how confident you are, talk about the parameter, make sure the parameter is either going to be the population mean or population percentage. It's going to be one of those 2. And make sure you talk about it in terms of the problem. So you'll see here I say the population mean number of personal computers per household, because that's what we're estimating. And then you want to say that is between whatever the values for the interval are, which in this case is 1.254 to 1.386. And that's a confidence interval question. There's one other thing I want to do with this question, and that is I just want to talk about what happens if some things change. So, for example, what happens if instead of being 95% confident, what happens if I want to be 99% confident? What happens if I increase my confidence level? So, when we did confidence intervals before, we weren't able to change the confidence level because we just used that estimate, which was always based on 95% confident. But you got to think that changing your confidence interval is going to have an effect. So you can see the questionnaire at the bottom. What happens to the confidence interval if we increase the confidence level? So there's a few ways to think about it. Let's just think about it mathematically first. If you think about it mathematically, the only thing that's going to change in here if you increase the confidence level is you're going to change that value of 1.96, that z value, to a value of 2.576. That value is going to increase because if you think about the picture, to be 99% confident, you need more of the area, right? So you got to spread out those z values so you get more area. Well, when you spread those out, you're going to get a wider interval. That's basically what happens. That 1.96, if it gets bigger, then that means your E value is going to get bigger because you're multiplying by a bigger number. When you multiply by a bigger number, your error tolerance gets bigger, your interval gets wider. So that's the short answer, is increasing the confidence level increases the error tolerance, giving a wider interval. So anytime you want to be more confident, your interval is wider. I like to also just kind of think about that because it makes a lot of sense if you really think about it. Because just think, if I'm 95% confident that the parameter is within a certain interval, and I want to be more confident, and I keep everything else the same, well, the only way to be more confident is actually to spread those values out, because if you include more values in your interval, then you're going to be more confident. That's basically the way it works. A wider interval has more values in it. It has values in it that the other interval didn't have in it. So when you spread that out, and you can think about the picture as well, you spread those values out, you're going to be more confident. You need a wider area to be 99% confident than 95% confident. That's the way it works. And if you just think about it in that way, it makes a lot of sense. Here's another way to think about it, which is important as we move into what will be the next topic that we cover in the next section. And that is this. When you do inferential statistics, you always have 2 kinds of error. In confidence intervals, you have 2 kinds of error. One is alpha, which is the probability of being incorrect. So, for example, if you're 95% confident, that means alpha is 5%. It's the probability of being incorrect. It's 1 minus your confidence level. You also have a second kind of error in confidence intervals, which is E, your margin of error or your error tolerance. So we have 2 kinds of error, alpha and E. So basically the way it always works in inferential statistics is we have these 2 kinds of error, and if you keep everything else the same and you just change one type of error, it's automatically going to change the other type of error because that error has to go somewhere. So, for example, if I just decrease alpha, then, well, that error has to go somewhere. So where it goes is it basically goes to E because that's the only other error we have. So if you decrease one type of error, really all you're doing is moving it to the other type of error. That's really what's happening there. So if you decrease alpha, then you're going to increase E. And that should make sense with what we just talked about. Because if I go from 95% confidence to 99% confidence, that means I'm reducing my alpha because it's going from 5% to 1%. If it goes from 5% to 1% and alpha decreases, then that means E is going to increase. And we just said E would increase, that margin of error is going to increase, and it's going to give you a wider interval. That's the way it's always going to work in inferential statistics. If you decrease one type of error, you're going to increase the other type of error. And of course, if you want to be more confident and you decrease alpha, it's easier to be more confident if you have a wider interval. So all of this really fits together. Once you wrap your head around it, it really does make a lot of sense. Let's look at what happens if we change the sample size. So this is something that we've talked about a decent amount in class, and it's something that's really important in inferential statistics. But what happens to the confidence interval if we increase the sample size? So the way that I recommend you think about these questions is just think about what effect does sample size have on error. And we've really talked about this a lot in here. And it only makes sense. If you increase sample size, that means you're getting more information from your population. Well, if you get more information, you have less error. That's the way it works. So basically what happens in a confidence interval is if you increase the sample size, then you decrease your error tolerance. Because the error tolerance is the thing that we calculate. It's the thing that's going to change. And if you think about it mathematically, notice the n in that formula, in the error tolerance formula E, the n is in the denominator. So when you increase a value in the denominator, you're going to decrease the quantity because you're dividing by a bigger number. So when you increase the sample size, you decrease the error tolerance. Decreasing the error tolerance means you have a more narrow interval. Make sure when you talk about how the interval changes, make sure you talk about it being wider or more narrow. Be careful about saying increasing or decreasing. If you say increasing, you need to say the width is increasing. So it's really the width that is changing. It's not like both values are increasing or both values are decreasing. It's really the width of the interval that is changing when you change these quantities we're talking about. So increasing the sample size gives you less error. Less error means a narrower interval. And that's a good thing to remember. Basically, less error means narrower interval. More error means a wider interval. And this is ultimately what we use in order to control error in inferential statistics. If you ever need to decrease your error, one way you can always do that is take a larger sample. The downside is it costs more money, but you can always decrease your error with larger sample sizes. One other one. You can see in that E formula there's basically three things. There's the Z, which is based on your confidence level. There is N, which is your sample size. And the other one is that sigma value. So what happens to the confidence interval if the population standard deviation is increased? Now do keep in mind that you have no control over sigma. Sigma is the standard deviation. The standard deviation is just simply going to be whatever it is. You're going to have to measure it, and you're going to have to deal with whatever that standard deviation is. It's not like the confidence level. The confidence level, you do have some flexibility there. You might choose to be 95% confident or 99% confident, but you can adjust your confidence level. You can also adjust your sample size. You can increase the sample size. You have some control over that. You're making decisions in terms of what that value is going to be. The standard deviation you have absolutely no control over. You just have to deal with whatever it is. But if you think about the standard deviation, if you do have more variability or a higher standard deviation is going to mean what? A higher standard deviation, remember, error comes from variability, so a bigger standard deviation means more variability, which means more error. More error means a wider interval, if you go back to what we just talked about before. Less error means a narrower interval. More error means wider intervals. That's always the way it works. So when we have more variability in our data, we're naturally going to have more error. So like I said, this isn't really something that you can control. You just have to measure it and deal with it. But basically what you end up with is when you have a lot of error or a lot of variability in your data, that means you're going to have to basically take a larger sample in order to counteract that increase in error, because a larger sample will decrease the error. So you can counteract it with a larger sample, and you can still get your error tolerance where you want. But the more error or the more variability you have in your data, the larger of a sample size you're going to have to take in order to counteract that and make sure you get your error down to where you want. And those are the three things that really affect the confidence interval. The three things are how confident you want to be, your sample size, and then how much variability you have in your data. So you should be able to calculate a confidence interval. You should be able to interpret it. And you should also be able to talk about these kinds of questions where we say, what happens if I change my confidence level, change my sample size, or change the amount of or what happens if I have more variability in my data or less variability. Okay, so let's look at a second example. So this one's a little different. Same idea though, we're still doing confidence interval. In a study of 517 music teachers, 403 say the video games, Guitar Hero, and Rock Band have a positive effect on music education. So we are going to construct, so we're first just going to construct and then we'll interpret. Construct a 99% confidence interval. Okay. So 99% confidence interval. So one thing that's changed, obviously, is in this case, we're not going to be 95%. We're going to be 99% confident. But there's one other big change in this case. When you read this question, it looks a little different because it says, in a study of 517 music teachers, 403 say video games, these video games have a positive effect on music education. So notice there is no standard deviation here. There is no mean. All we're basically given is 403 out of 517. So when you read that problem, you have to recognize that this is not a mean problem. The big indicators is there is no standard deviation, and of course, it doesn't give you any kind of mean. Instead, it basically says 403 out of 517. So that tells you this is a proportion problem. So we have to use different formulas here since we're dealing with a proportion. So as always, just start with what you need. You need to start with a proportion problem of start with your sample size. Our sample size is 517, and then you need your sample proportion. So the sample proportion will sometimes be given to you. Sometimes you'll actually have to just divide in order to get it. So here we have to divide. We know that 403 out of 517 believe that these games will have a positive effect. So that means our proportion, our sample proportion, our p hat value, that's what we call that. I call it p hat. P with the caret on top of it. That's what most statisticians call it. P hat is going to be 0.779 here. So that is our statistic. We have our sample size. That's everything that we need in order to calculate a confidence interval for a proportion. So when you're dealing with a proportion, the error tolerance formula is different. It's the same idea. It's z times the standard error, but the standard error for a proportion is that square root of p times quantity 1 minus p over n. And of course, we're going to estimate p by p hat. So whenever we go to do this problem, since it's 99% confidence, that means our z value is now going to be 2.576. And again, that comes from that list of values that I gave you back on an earlier slide. The standard error is that square root. So we take the square root for p hat, we plug in what we just calculated to be, which is 0.779. And then we plug in 517 for n. And then we crank through the math here. So when you do this mathematically, do be careful. Make sure you do your order of operations correctly. Sometimes people have trouble getting their order of operations correct, and they make mistakes on these error tolerances with proportions. So it doesn't hurt to just take a minute and make sure that when you work through that math, you get what I got, which is 0.047 when you round to 3 decimals. So when you do that error tolerance calculation, make sure you do under the square root stuff first. So make sure first you just take 1 minus 0.779, then you multiply that by 0.779, then you divide by the 517, then you take the square root, and then you multiply by the z of 2.576. You do that last once you get the standard error, and if you go through that process, you will end up with an error tolerance of 0.047. Once we get that error tolerance, now we can create our interval. So our statistic here, since we're dealing with a proportion, is of course p hat. So we're going to take our p hat value and add and subtract that error tolerance we just calculated. So we're going to take 0.779 plus or minus 0.047, and that will give us our interval. Our interval here is 0.732 to 0.826, or if you prefer, you can write this as a percent. You should be able to switch back and forth between decimals and percents. Most commonly when we interpret these proportion problems, we're going to interpret them as percents because that tends to be what the average person understands a little better. So we're going to say the percent is between 73.2% and 82.6%. So now let's actually interpret the interval. So the interpretation, very similar to what we did on the last one. All these interpretations are the same. Start with how confident you want to be. We're going to be 99% confident that the population proportion of music teachers who think these video games have a positive effect on music education is between these two values of 73.2% and 82.6%. So something like that. Doesn't have to be word for word what I write there, but you should make sure you have the main components, how confident you are. Make sure you talk about the population percentage or population proportion, and make sure you talk about it in the context of the question. And then, of course, make sure you say that you are confident that is within that interval. And those are the components that you need in order to interpret a confidence interval. So something like we are 99% confident the population percentage of music teachers who believe the video games have a positive effect on music education is between 73.2% and 82.6%. And those are the big things in this section. The big things in this section are confidence intervals and interpretations for both means and proportions. Those are the big problem kinds of things that you got to be able to do, along with understanding what happens when you change some of the quantities. There is one last thing I want to do before we call the end to this lecture. I just want to show you, since we talked about 1 over square root of n at the beginning of the class, I just want to show you where that formula comes from. Not that you really have to know this. I would never ask you to show me this, but I do just want to show you where that 1 square root of n comes from in case anyone's interested. So why did we use 1 over square root of n to estimate error tolerance for a proportion? Okay, so if you remember, whenever we used 1 over square root of n, we said you're always 95% confident. We also said it's a conservative estimate for margin of error, meaning that it will sometimes be too high, but it will never be too low. And the reason being is because we assume a maximum amount of variability when we use 1 over square root of n. We're basically figuring out what the most possible variability is, and we're using that. So this is used for a proportion. So the variability for a proportion is essentially just p times 1 minus p, or to estimate it, p hat times 1 minus p hat. So what I did was I just created a table here so that you can see kind of what happens as you pick some different p hat values. And of course there's an infinite number of possibilities for p hat, but I just picked some simple ones so that you can see where the variability is maximized. And you can see that if p hat is 0, then the quantity p times 1 minus p hat, this is the variability, is also 0 because it's just 0 times 1. If p hat is 0.1, then you get 0.1 times 0.9, which is 0.09. So you can see, obviously, it went up. If you go to 0.2, you get 0.2 times 0.8, which is 0.16. It's still increasing. 0.3 is 0.3 times 0.7, which is 0.21. If p hat's 0.4, you get 0.4 times 0.6, which is 0.24. The most variability you can ever have is when p hat is 0.5, because then you get 0.5 times 0.5, which is 0.25. And then, of course, when you get past 0.5, it's just going to start going the opposite direction. So if you look at that table, you can see that the maximum amount of variability you will ever have in a proportion is when the proportion is 0.5, because you get actually a variance of 0.5 times 0.5, which is 0.25. So that's the most variability you can ever have. So if we think about that in the context of our error tolerance formula, we know that this error tolerance formula works. This is the error tolerance formula that we use for a proportion. Then what we can do is we can assume, well, let's consider a maximum amount of variability. We just said a maximum amount of variability is 0.5 times 0.5. It's when p hat is 0.5. Well, 0.5 times 0.5 can also be written as just 0.5 squared. So when you take the square root of 0.5, when you take the square root of 0.5 squared, the square root and the square just go away, and you're just left with 0.5. So the numerator of that just becomes 0.5, and the denominator, we still have the square root, so we get 0.5 over square root of n. So the next step is kind of where the 95% comes into play. For 95% confidence, we just said z is 1.96. To be a little more general and to estimate a little more, 1.96 is approximately 2, which is like what we say on the empirical rule. So I do use the approximate symbol there. So we're actually overestimating it just a touch here as well, because 1.96 is rounded actually up to 2 here. So we're going to get just a little more error tolerance than what we would if we used 1.96. But that value of 2 makes this work out nice and neat, because we just take 2 times 0.5, which gives us 1. And we get 1 over square root of n, which gives us a good estimate for a proportion. This estimate really works well if the proportion is close to 0.5, where it's close to having a maximum amount of variability. And obviously it's not going to work as well when your proportion is close to 0 or 1, because then you have a lot less variability. You don't have to know that. It's not like I would ask you to explain where 1 over square root of n comes from, but that is where it comes from. It overestimates the amount of error a little bit, but it is a good place to start in order to understand confidence intervals, and that's why we covered it. So that's it. That is the end of section 4B.